Well, good afternoon. It's already 12:24, and there's still nobody in the classroom. I had two students come by and an instructor come by, so I'm late getting started. But we are started now. Last time, let's see, let me tell you this one announcement. I don't know if it will matter to anybody, but I do have an appointment for an infusion on Friday. So normally on Fridays I'm on the Birmingham West campus from 8 to 12. Hold on just a second. Sorry, the instructor who came by didn't close the door, and I didn't want to bother people elsewhere. So I do have normally I'm on Birmingham campus Fridays from 8 to 12, Birmingham West campus. But this Friday I've got an infusion scheduled, and I can't remember what time it starts, probably right at 8 o'clock, so I wouldn't be able to get to campus anyway, and it usually goes well into the afternoon, if not most of the day, so I will not be on campus at all on Friday, on either campus, so I will not be there. Now, next, I guess that's all the announcements. Where we left off last time was in Chapter 13, which is functions of several variables, and we're in 13.4, which is talking about differentials. And on page 905, we had just given the definition of differentiability, and example 2, just following that, is where we start today then. Show that the function f of xy, which is x squared plus 3y, is differentiable at every point in the plane. Okay? In other words, the plane, xy plane, where the domain of this function is, because you see, in a single variable function, f of x, y is equal to f of x, then your domain is the x-axis, okay? You know, where on the x-axis is this function defined? Well, when two variables, where on the xy plane is it defined? Because x and y are both independent variables, and they can vary anywhere they want to. So now the domain is where on the plane is this function defined. And just looking at that, you know that you can take any value x and square it, and you can take any value y and multiply it by 3, and you can take any combination of those and add them together. So that would be it anywhere. But using the definition, which we did last time, let's go back and review it just quickly. Function f given by z is equal to function of f of y is differentiable at any point x0, y0 if delta z can be written in the form of delta z is equal to the partial of f with respect to x at x0, y0 times delta x plus the partial of f of y, x0, delta y, plus some epsilon delta x, epsilon 1 delta x, epsilon 2 delta y, where both the epsilons approach zeros as the delta x and delta y's approach 0, 0. In other words, as those increments are getting smaller. Function f is differentiable in a region R if it's differentiable at each point in R. So, we're now to show this is differentiable at every point in the plane. Okay? Well, if we start with, let me get my pen set up. Okay? Z is equal to f of xy. That's where the function was in that definition we just had. So let that be the case. Then the increment of z at any point xy in the plane, that's your delta z, small change of z at any point there, must be, well, the definition of that, and we talked about this last time, is f of x plus delta x, comma, y plus delta y. That's when the delta z is the change of the f value when you change the x just about a little bit and the y by a little bit. Okay, that's what that stands for. Minus where it was to begin with, f of xy. Okay, so where z is f of xy, okay, pick an x, pick a y, you go there, you find the z, okay? One and only one z, that's what makes it a function, okay? Now, and that's what your value, function value is at xy, that value of xy. Then, move the x just a little bit and the y just a little bit, that's going to give you a new z, okay? And the difference between those two z's is your delta z, which would be the f of x plus delta x, comma y plus delta y, that new z that you had, minus the old z, f of xy. That's your change of z, delta z. Okay? Now, here, our function, f of xy, is this function right here. So, f of x plus delta x would then be this one right here. Put a x plus delta x everywhere you see an x here. Okay, so that would be x plus delta x squared plus 3 times your y is now a y plus delta y. Okay, minus x squared plus 3 y. Okay, that was your original f of x. Okay, well, what is this? This is your x squared plus 2x delta x plus delta x squared plus 3y plus 3 delta y, and subtract from that x squared and subtract from that 3y. Okay, that will give you your delta z. Well, the x squareds go out and the 3y's go out. Okay, they subtract to 0. So your delta z is 2x delta x plus delta x squared plus 3 delta y. Okay? Now, to get this into the form, now here's the form we're looking for, this form right here. If you can express that delta z in this kind of form, then we'll be in good shape. Okay? Well, this, so let's, oops, went the wrong way. Okay, so we need something, let's review what we want. Some function, delta x, some function delta y, and then some epsilon delta x and epsilon delta y. Okay? So this will be 2x delta x plus 3 delta y, that took care of this term and that term, plus let's see. Went the wrong way. We have an epsilon 1 delta x plus a 0 delta y, because there aren't any delta y terms here. Well, the reason I broke this up like this, what is f sub x? That's 2x, exactly what this is. And what's f sub y? That's 3. Okay? Exactly what this is. Okay? Now that leaves us an epsilon 1 this epsilon 1 would be a delta x. Okay? and the epsilon 2 would be the 0, okay, because there is nothing there, okay? So there is some epsilon 1 and epsilon 2 approaching 0 as the delta x is approaching 0. So this is your f sub x, delta x, plus f sub y, delta y, plus epsilon 1, delta x, plus epsilon 2, which has to be 0, delta y. Okay. So you've done it. Epsilon 1 is delta x, epsilon 2 is 0. And both of those approach 0 as delta x and delta y approach 0 separately. Okay? So therefore f is differentiable at every point in the plane. And the graph of f is shown in the figure, which I'm not sure they show, but let's see if they do. So let me erase all my scratch here. And I think you'll see they do almost the same thing because I was sort of following their lead on it. Let z be f of xy, which is exactly what we have up here, x squared plus 3y, okay? And the increment of z at an arbitrary point xy, any old point xy, would be delta z is f of x plus delta x, comma y plus delta y, minus f of xy, that's your change of z. Well, your f function tells you to take whatever's in parentheses for x and square it, so that's x plus delta x squared, plus 3 times whatever's in the parentheses for y, which is y plus delta y, minus the f of xy, which is x squared plus 3y. Okay? When you multiply that out, just like we did, x squared plus 2x delta x plus delta x squared plus 3y plus 3 delta y minus x squared minus 3y. And notice the x squareds go out, the 3y's go out, and that leaves you 2x delta x plus x delta x squared plus 3 delta y. Okay, rearranging the order slightly and a little bit of a substitution. That would be 2x delta x plus 3y delta plus 3 delta y plus a delta x times a delta x plus a 0 times delta y, and that's exactly of the form f sub x of xy delta x plus f sub y of xy delta y plus epsilon 1, if that's delta x times delta x, plus 0, but that'd be your epsilon 2 delta y. Okay? For epsilon 1 delta x, epsilon 2 is 0. And here's the graph. Okay? Because epsilon 1 approaches 0 as delta x approaches 0, obviously because it is delta x, epsilon 2 approaches 0 as delta y approaches 0 because it is 0. It's always 0. Follows that f is differentiable at every point in the plane, and the graph is shown here. Now, to get a better image of that graph, let's go back to the original function, x squared plus 3y. Well, let's start with that f being 0. Then you'd have 3y is equal to minus x squared. Okay? And if you look at the graph here, it's really hard to picture. Here, if when z is equal to 0, f of xy is equal to 0, you have a parabolic-like form, and I think it is exactly a parabola. Let me look at it one more time. Yeah. Y is equal to 1/3 x squared, okay? Minus 1/3 x squared. So, if you look at this, if you just look at the xy plane, when z is equal to 0, you see that does, graph, oh, goodness gracious. The way they've tilted the graph and stuff like this, it's really hard to see easily, but that would form a parabola opening downward because of the minus sign, and it's a pretty wide one. That's what makes it sort of hard to see here. I don't know why they... Okay, I think I was picturing this is coming out. This is going back that way, so it's a very wide parabola opening downward away from us, okay, and in the negative y direction, okay. All right, and then subsequent to that, you go up or down. So it's kind of like, I think it would be called a cylinder, an open cylinder that maps that parabola up and down infinitely. It's kind of a going back here to see. Okay. If you look where x was 0, then you do have in the yz plane, you have a line z is equal to 3y, so it's very steep. And if y was equal to 0, z was equal to x squared, so that's a parabola in that direction. So let's see if we can kind of imagine those and map them in. X is 0, meaning you just got the YZ plane. Yeah, you can see that goes, you might not be able to see it exactly, but it's a line that goes through the origin. And it has a slope of 3, so it goes up pretty steeply. Y is equal to 3. Is that how we set it? 3z. All right. And then the other way, if you let y equal 0, then you get, it's really not really obvious from this rendition here that you would get a parabola, but the formula says you would. Okay. Now, that's enough of that. Be sure that you see the term differentiable is used differently for functions of 2 variables than 1. Function of 1 variable differentiable at a point is when its derivative exists at that point. For a function of 2 variables, however, the existence of the partial derivatives f sub x and f sub y, partial of f with respect to x and partial of f with respect to y, do not guarantee that a function is differentiable. Okay, and we're going to do that in example 5. The next theorem gives a sufficient condition for differentiabilities of a function of 2 variables. So here it is. All right. If f is a function of x and y, and f sub x and f sub y are continuous in an open region of R, then f is differentiable on R. So f sub x and f sub r are both continuous on that region R, then the F is differentiable there, okay, on that region. Every point in the region where F sub x and F sub y are both continuous. Okay. Now, what to do with that? Somehow I got all my pages wrinkled in my book. Now we're going to do approximations by differentials. Okay. Theorem 13.4, which was not that last, no, the very last one, that sufficient thing, tells you that you can choose x plus delta x and y plus delta y close enough to xy to make epsilon delta x and epsilon 2 delta y insignificant. In other words, for a small delta x, delta y, you can use an approximation that your delta z is going to be approximately the same as your dz. Okay? And that approximation is illustrated here. I don't know how well it's illustrated, but let's see what we can do. Okay. The tannish kind of curved shape here is our function z, I'm pretty sure. Okay? Okay. All right. Now, let's just imagine this is a really blown up example, because these look like they're not insignificant differences here. All right. Your okay, that's not what I was looking for. Okay. So your actual function value z is on this tannish kind of surface. That's probably the best word for it. Here's the point xy, somewhere in the xy plane. Okay? If you do an x plus delta x, it shows the delta x being slightly negative, and there's the y is the same value. And then your delta y is a positive value here. You're going increasing in the y. So okay. All right. Okay. Then, if you change your x a little bit, then that's where this is bizarre. This dot here is not on the tan thing. It's on the green plane here. Okay? Then if you increase the y a little bit from that same delta x, now you're going up to here. Okay? So here is the that's what they call the delta, no, the dz is way up there. Okay, the delta z, how much z actually changed when you increase x this much and then y this much, is right there. Okay? Well, glad you showed.
Yeah, I thought about it.
Took you a while to think, wasn't it?
Yeah.
Okay, let me get the projector on. And there's students here, I'll say a little bit of lights here. I was just trying to explain, pretending there were people here to explain to what was going on with this, and it's really hard to do when there's nothing to bounce off of. So it's coming up here. And we've already introduced, go back a little bit further. It's the last thing we did last time. The delta Z is when you change your F a little and your X a little and your Y a little, and how that changed the function, okay? Now, the DZ we don't have a good picture of, and that's part of the problem that I was having, trying to think of a good way to explain this approximation by differentials. Okay. It says as long as the delta X and delta Y are both small. Now remember, X and Y are both independent variables. Z depends on them. Okay? So what the deal is here, you start with this point x, y, and you have a function value here. This is f of x, y. Okay, that's your z value. Okay? Now, you change x a little bit, x plus delta x, and this delta x is obviously in the negative direction, which is fine. But keep the same y, and when you do that, and again, this is there's a part of this that sort of, this seems just absolutely backward to me, and it always has, and I guess it always will. This is the function, the tan sheet. Now, it's a curved surface. That's the z values. The estimated z's, the approximated z's by your differential, they say the exact change in z is this. Well, to me, that's an approximate change because you're changing here, you're changing there, and you're approximating that by a plane. So this is the x plus delta x, y on the plane. Okay? And here's Muhammad. Okay. Are you sure they got you back in now?
And not fully. Yeah.
Huh?
Not fully. Not fully.
Not fully yet?
No.
Okay.
They told me they said they did the changes. They said just waiting for them to finalize.
Okay.
I already received an email that it should finalize tomorrow.
Oh, tomorrow. Okay. All right. Well, when they put you back in, then I'll have to go back and fill in the attendance because you're not showing up on attendance at all now. So I guess after tomorrow you will.
That's okay.
Yeah. Okay. So here we're talking about differentials. Okay. And here's the part that bugs me. Okay. Over here, when they give the definition of differentials, what they say, definition of differentiability, okay, is that the delta z is written this way. Well, the delta z, a function given by this, is differentiable, and if delta z can be written this way. So That to me is an approximate change. Okay, it's not exactly the same. This is your partial of L times some incremental change, so the partial Y incremental change, and then plus a little bit of other error things. This to me is not the actual, this is the approximate, in my mind, when I look at this. But then when they come over here, they're calling not this the differential, but that the differential, okay? And it just seems like it's a little bit backward to me. To me, this is the actual, that's the approximate. They're acting as if it's not. They're saying that the delta Z is the actual change in Z, whereas the differential, the dZ, is this approximated change, which to me just seems backwards, okay? But that's exactly how they describe it, and it seems like it is, because this is a plane approximation to a curved surface, okay? And it's saying that for very small delta X's and delta Y's, you're not far off. When you get further off, further away, then the changes can be fairly significant, okay? And here they're saying this dz is this partial of z with respect to x plus the partial of z with respect to y. But that's what they were calling delta z in the previous slide. And it just seems like, to me, they've got them backwards here. But this is what they say. So as long as you can just keep up that one's one and one's the other. But it just seems like they flip the notation on us. Okay? So anyway, the partial derivatives, partial of z with respect to x, is how much z has changed with a small change of x. Okay? Now they're saying that dz, now they're saying that is the differential, which in an earlier slide, it was a delta z there. So, well, maybe not, because the delta z had those epsilons in them, and this doesn't. So I guess that's the difference, okay? But the partial of z with respect to x, partial z with respect to y, can be interpreted as the slopes of the surface in the x and y directions. And if you go back here, you see that is what you've got here. How much does, okay, remember your x direction is this way, y direction is that way. So how is x changing when you go from x to x plus delta x? That's in the negative direction. Well, that's, the function is going uphill there, which means in the positive direction it would be going downhill in the x. But in the y, going from y to y plus delta y, that would be the change here. That's definitely a positive slope in that direction. So it's a downward slope in the positive x direction, an upward slope in the positive y direction. It would be something like this. So that's your slope here. This is your slope here, but you see that's in the negative delta x. So the delta x is a negative value, that's a negative, so that's what makes that positive. So it's a little bizarre. Now, the actual change of z would then be from here to there. And you do your change of x, which gets you back to this point. This point here is on the green slope. This point here is that corner of the hand surface. It's on the green slope too, but it's behind the green slope. It's under it. It's there, and then here is the one here. So this is your actual delta z in the x direction. That's your delta z in the y direction. That's your total delta z. Here is your dz. This they just call this. This is the slope times your delta x, and that's your slope times your delta y. So that puts it on the plane. Okay. Now, so the partial derivatives are those slopes. That means that dz, now they're calling that dz, is partial of z with respect to x, delta x was partial of z with respect to y, delta y. That represents the change in the height of the plane that is tangent to the surface at the point, alpha of xy. because the plane in space is represented by a linear equation in x's and y's and z's. The approximation of delta z by dz is called a linear approximation. Now, we did this back in single variable calculus. We talked about these as well. Now we're two-dimensional. So it's not just a line, it's a plane. Linear in both x and y dimensions. Okay. So here's example 3 on page 906. Now, in addition to being on your slide set here, you can also go to larsoncalculus.com for an interactive version of this type of an example. Now, so it says use the differential dz to approximate the change in z equal square root of 4 minus x squared minus y squared as xy moves from the point 1, 1 to the point 1.01 and 0.97. So notice your change of x is 0.01, your change of y is a negative 0.03. Okay? And compare that approximation with the exact change in z. Okay? So let's first do our dz. Okay? And how did we define dz? There it is. Partial z with respect to x delta x plus partial of z with respect to y delta y. So that would be partial of z with respect to x times your change of x plus partial of z with respect to y times your delta y. Okay, now, I said it, but let's write it down. If you're going from here to there, the delta x is what? If you go from 1 to 1.01, what's your delta x? 1 to 1.01. Second? What's your change of x there? If you go from 1 to 1.01. It's 0.01. Is that what you said? I can't hear. You see? Yeah. Okay. What's your delta y? You're going from 1 to 0.97. That's what?
0.97.
No. What's the change? 0.03. That's the change of y. Your change of x from there to there is 0.01, and the change of y from there to there is minus 0.03. You see? That's how much it changed. Yeah. Okay. All right. So, what we have to do, is calculate our partial of z with respect to x. So what I'm going to do is I'm going to rewrite this as 4 minus x squared minus y squared to the 1/2. I like taking derivatives of exponential notation rather than radical notation. It's just easier to do. So what's the partial of z with respect to x? Help me out here. You do the outer function first, 1/2. The inner function, 4 minus x squared minus y squared. But drop this by 1, you're taking a derivative, right? So that would be to the minus 1/2, right? Okay. Then you got to chain rule it, but only with respect to x. And that would be times a minus 2x. This is a constant. You treat that as if it's a constant. Okay? So the 2's are going to go out, and that's going to be a minus x over the square root of 4 minus x squared minus y squared. Because actually the minus 1/2 moves it downstairs. That's your partial of z with respect to x. So your dz, the differential z, is equal to that thing, minus x over the square root 4 minus x squared minus y squared, times your delta x, 0.01, plus, now we got to do the partial of z with respect to y. Partial of z with respect to y. Almost going to be the same thing, isn't it? It'd be 1/2 4 minus x squared minus y squared to the minus 1/2 times a minus 2y. Okay, again, you treat 4 as a constant and you treat x as if it's a constant. And again, your 2's go out, and then you're going to have, rather than a plus, that's going to be a minus. Minus, this time it's y over the square root of 4 minus x squared minus y squared. Okay? Times your delta y, which is a negative 0.03. So how much is z change there? Now what we do, we plug in the original values, 1, 1. Okay? That's going to be a minus 1 over the square root of 4 minus 1 minus 1, which is square root of 2, right? Okay? Times 0.01. And you got a minus, which is going to be a plus 1 over, same thing, square root of 2. All right? Times 0.03. I've already taken care of the minus sign, but we still got the number there. Okay. Now, looks like time for a calculator to me, and see how much the z has changed. Okay. Negative 1 divided by the square root of 2 times 0.01 plus 1 over root 2 times 0.03. Pretty obviously the positive's going to win here, but by how much? Anyone got it yet? One, yeah, that's what they got in the book. 0.0141. Okay? My guess is that's just a multiple of root 2. Now, a little bit easier way to have done this would have been to factor out the 1 over root 2. And then it would have been 0.03 minus 0.01, 0.02. Okay. And that would have been a little bit easier to do the calculation. But you get the same thing. So it's 0.02 over root 2. Okay. Which is 2 decimal places moved from 2 over root 2 to 1.414. Okay. Now, that's your approximation. Use the differential to approximate the change. Compare the approximation with the exact change in z. So the exact change of z is what we call our delta z. And how you do that is just, yuck. It's going to be a little hard to do on here, but we can. Z final is going to be the square root of 4 minus 1.01 squared, that's your actual x value, minus 0.97 squared, that's your actual x2, and then subtract from that the square root of 4 minus 1 minus 1, which is root 2. Okay? So, you would, again, with your calculator, do this. And if you do the square root key, opens the parentheses, 1 minus 1.01 squared minus 0.97 squared equal, or close your parentheses, minus root 2. Let's see what you get. Okay. So square root of, that opens the parentheses for you, right? On your calculator? Or it depends. Will you have a scientific? Or is that display type?
Yeah, it's a scientific. But,
okay, in the scientific calculator, you may not be able to do that. Okay. Well, I think, yeah. Okay, what you have to do is enter the argument first. That's what I was wondering. Okay, so you enter this first. 4 minus 1.01 squared minus 0.97 squared. Hit an equal sign. Okay, it should be a number fairly close to 2.
what I have is negative 0.95.
Wait. Let me see the difference. Let's start with 4 minus 1.01 squared. Squared, yeah, minus 0.97 squared. Yeah, just a little bit. Now take the square root of that. What you get when you take the square root of that? What do you get when you take the square root of that?
I have 1.42.
Really? Oh, wait, I'm sorry. You're supposed to subtract square root of 2 from that. I'm sorry, go back, square that again, okay, and subtract the square root of 2 from it. I forgot to tell you that part. Or we can start over. Want to start over or not?
Yeah, I don't know how to do that.
Okay. Start over from scratch. 4 minus 1.01 squared minus 0.97 squared. Okay, equal. Take the square root of it.
Just take the square root.
Yeah. She gives you something, huh? Okay. Now, about 1.4 something, right?
Yeah.
Okay. Minus the square root of 2. 2 and then do a square root sign. Equal.
Okay, 0.01.
Okay, say that again.
0.0136.
0.01 what? 36. Okay. So that was the actual change. This was your differential change.
37.
Huh?
37.
37? Okay, sorry. Okay. Whoops, where'd it go? There it went. Okay. All right, so how much were they off? 0.0004. Okay, not too far off. Okay. 0.01 and 0.03, you're 0.0004. 3 zeros and 4. So pretty reasonable. Okay? Got it. Okay, and that's what the book got to. Now, a function in 3 independent variables. Let's see if they have the, let me get out of this and show you how they did it. Sorry. All right. Letting x, y be 1, 1, and x plus delta x, and y plus delta y be 1.01 and 0.097 produces the dx equal delta x of 0.01 and dy equal delta y of negative 0.03. We did those, right? All right. So the change in z, the approximated, the dz, is then the partial of z with respect to x dx plus the partial of z with respect to y dy, which is, and there's the partial, which we did, they didn't do them separately, times delta x. And see, drives me nuts, is to go back and forth with deltas and d's. They wrote it as d here, but wrote it as delta there. This is exactly the same. It's okay, but it's just a little nut seeming that they can't stay on one script, okay? And that's exactly what we got. And when x and y are equal to 1, the delta z is that they never do actually finish the problem. And again, now they're calling that delta z rather than dz, okay? That's 0.0141, exactly like we got, right? Okay? And then they didn't even show the record, the next part. Sorry about that. They don't even show the second part. Sorry about it. Woo. They just leave you hanging there. Oh, wait, maybe so. Or maybe this is all part of it. Okay, sorry about that. Yeah. In figure 1336, you see that the exact change corresponds to the difference in the heights of 2 points on the surface of the hemisphere. And do I see where they're talking about there? Not much. Boy, what a... okay, they show these as the same points here. There are really 2 points there, and then 2 points up here. This one's 1, 1, and this is 1.01 and 0.97. So your x has come out just a little this way, the y is going back that way just a little bit. You can't tell a difference. So they blew it up here, and this was your first point, xy. There's f of xy. Here's the second point, x plus 0, 1, which you came a little bit this way, but you went back 0.03, and then there's your f of x plus delta x, y plus delta y, the actual one there. And they show that changes the point about 0.0137 of that value is that, whereas the other one was 0.0141. So, wow, not a very good picture there, but I understand what they're doing there. The difference is given by this, okay? And you did that calculation and came up with 0.0137, 0.0137. And so the other gave you 0.0141. So not much of a difference at all. Now, a function of 3 variables, 3 independent variables, f of x, y, and z, is differentiable x, y, and z, provided that your change in w, delta w, is equal to the f of x plus delta x, y plus delta y, z plus delta z, minus f of x, y, z. Okay? That's your actual change in your W. Evaluated at your original point, evaluated at your slightly changed point, and that should be able to be written in the form of f of x delta x, partial of f with respect to x delta x, partial of y with respect to delta y, partial of z with respect to delta z, plus some little error bars there, where these errors all approach zero as the deltas also approach zero. Because as you get closer and closer, the errors should get smaller too. With that definition of differentiability, theorem 13.4 has the following extension for functions with three variables. If f is a function of x, y, and z, where f of x, f of y, and f of z, that is partial of f with respect to x, partial of f with respect to y, and partial of x, f with respect to z, are continuous on the open region R, then f is differentiable on R. Blah, blah, blah. Okay. So, as is true for a function of single variable, when a function of two or more variables is differentiable at a point, it's also continuous there. You can't have it, if it's differentiable at a point, it must be continuous. Because if it's discontinuity, how could it be differentiable? You just can't have that. So, differentiability implies continuity. Continuity doesn't always imply differentiability. You can be continuous like this, but if you have two different slopes, one here and one there, that's not differentiable at that point. Differentiable before that and before this. But if it's differentiable, it's got to be continuous. So if a function x and y of x and y is differentiable at x0, y0, then it has to be continuous to x, y0, x0, y0. Must be. No way around it. So here's a function, f of xy. It's defined to be minus 3xy over x squared plus y squared. That's any time x and y are not equal to 0. If x and y are equal to 0, then it's defined to be the value 0, 0 alone. Okay? Now, it says show that the partial of f with respect to x exists at 0, 0, and the partial of y f with respect to y exists at 0, 0, but the f is not differentiable at 0, 0. Okay? So we've got to do our partials first. So let's do the partial of this one. F sub x. What is it? Using this top form here. Oh man, what kind of rule is that? To do a derivative. What kind of rule do we have to have? Second? Looks more like a quotient to me. Okay. How does the quotient rule go? There's an easy little, almost sing-songy thing that does it. Low d high minus high d low over low low. Remember that? Okay. So your low here is your x squared plus y squared. Okay. D high, which would be, and it's taken with respect to x now, minus 3y, right? Minus high d low, that's a minus 3xy, times the derivative, now with respect to x alone, to x, right? Divided by x squared plus y squared squared. Right? Yay or nay? Okay. Now, they say, does this exist? And frankly, I don't see how it could. Because you still got 0 in your denominator. Well, let's work it out and see if anything seems like it. I just don't see how it could. It's still an indeterminate form. Oh, wait. I just noticed. We skipped example 4. So I have to come back and get example 4. I see what they're saying here, with the exception of it looks like an indeterminate form, not a that the derivative is 0. 0 minus 0 over delta x is approaching 0 still seems like an indeterminate form to me. But here is the key, and this basically says it all. If you take this function and let it approach 0, 0, okay? Let's first let it approach as x equals 0, but y is not. That would be going to 0. And as y approaches 0, but x not 0, then that's going to 0, okay? But, say, along the line y is equal to x, if you're approaching that 0, that would be approaching 0, and both of these would be approaching 0. Okay, wait, so back off. Yeah, no, what I said was first. The other said is y approaches x. The limit is this. Oh yeah, okay. If y is equal to x, so you're approaching along that line, this would be minus 3x squared over 2x squared, right? And the x squareds cancel out, you get minus 3 halves, okay? Now, if you allowed it to approach 0, 0 along the line, this is along x equal, or y is equal to x. If you went along the line y is equal to negative x and approached it that way, then you would have positive 3x squared, because y is negative x, and this would be over 2x squared, and that would be going to 3 halves. Okay? One's going to negative 3 halves, the other's going to positive 3 halves. The limit can't exist. Okay? Now, what they say next, though, about the partials existing, I just don't buy. I don't see how they could exist. Unless you do L'Hopital's rule or something like that with them, I don't see how those two exist. So anyway, this is enough to show that they're not differentiable. The derivatives, the functions are approaching different values in different directions. We skipped the example 4, so let's go back and do example 4. Okay. Let's do it here. The possible error involved in measuring each dimension of a rectangular box is plus or minus 0.1 millimeter. That's pretty close, okay? The dimensions of the box are, so the potential error of each dimension is plus or minus 0.1 millimeter. Okay. Wow. The dimensions of a box are x equal 50 centimeters, y is equal to 20 centimeters, and z is equal to 15 centimeters. But the possibility of error in any case is 0.1 millimeters, okay? Which would be 50 centimeters, and a millimeter would be 50.0 millimeters, and 1/10 of a millimeter would be 50.01, 20.01, 15.01, or 49.09, or 19.99, and 14.99. So that's pretty close, okay? All right. Now, use dV to estimate the propagated error and the relative error in the calculated volume of the box. Okay? So the volume of the box is length times width times height, x, y, z. Okay? The dV would be partial of v with respect to x, delta x, plus, or dx, whichever you want to do, partial of v with respect to y, delta y, plus partial of v with respect to z, delta z. Okay? What's the partial of v with respect to x? If there's your v, what's the partial of v with respect to x? Partial of v, there's your v, with respect to x. YZ, exactly. So this would be YZ times delta x plus, and what's partial of v with respect to y? Second, xz delta y plus partial v with respect to z, xy delta z. Okay? Now this would be y times z, that would be 300. And the delta x, are they going to use plus or minus 0.01? 0.01 centimeters, okay? Okay, because that was in centimeters, okay? Plus xz would be 750 times plus or minus 0.01 centimeters, plus xy, which would be 1,000, wouldn't it? Yeah. 1,000 times plus or minus 0.01 centimeters. Okay? Well, move this decimal 2 places. That would be 3 plus, move this one 2 places, 7.5. And this is plus or minus, by the way. Plus or minus 10. Okay? So, looks like to me that would be 20.5 cubic centimeters. Okay? Now, that's out of, if you multiply those three together, that gives you 15,000. Okay? So plus or minus 20.5 out of 15,000 is not bad. Okay? 20.5 cubic centimeters. Okay? Use the dV to estimate the propagated error and the relative error in the calculated volume of the box. So what is relative error is the actual error plus or minus 20.5 cubic centimeters. Now, I was given it to you before, divided by 15,000 cubic centimeters, and do that on your calculator. 20.5 divided by 15,000. Okay, let's see what they got. Give me one more decimal digit. 3 what? Huh? 3 what? Okay, let's round that to 4. And that's what they got. And they call that a plus or minus. Okay. Yes, sir. What's that? Yeah. Oh. Okay, yeah.
But that's okay. I don't have to set up yet. So
okay.
Go ahead.
Okay.
We're supposed to start.
What do we got? We've got, what, 15 minutes?
Yeah, that's fine.
Okay. Okay. All right. That speech class met the first day and hasn't met, is the second mini term?
Yeah.
Hasn't met since, and now showed up again today.
That's what my class is, my physics class.
Yeah. Right.
No speech class.
So they're going to have to move here, but they don't start until 2, right?
Yeah, it's 2.
Yeah. So at 2 I get out of here and they come in. Yeah. Okay. So at 1:55 we get out of here. Okay, so that's plus or minus 0.14%. And that's what they got. Not bad. I mean, 20.5 cubic centimeters might seem like a lot to you, but out of 15,000, that's a pretty small percent error. Okay. Now, that was example 4. And we just finished, well, we were doing example 5. So let's go to example 5. Okay. I was doing it. Let's see how they did it. Okay. Now there's the drawing of example 5. Man, what a mess. I'm glad they didn't have me draw it. You can show that f is not differentiable at 0, 0 by showing that it's not continuous at that point. See it's not continuous. Look at the values of f of x, y along 2 different approaches shown in the figure. Okay. Well, I did it by 3. I did it either the x or y axis. Well, but then they showed it along the line x equal y is equal to x. So then you plug in instead of y x, that would be minus 3x squared over x squared plus x squared. That would be minus 3x squared over 2x squared. That would be minus 3 halves. So if you did along the line, where is that line? why they show it way up there, I'm not sure. Oh, there's the origin. So that line better pass through the origin. So it's somewhere down there. No, that's this one here. But it should be coming out of the origin there. And there the f of x, y approaches 3/2. But then when you go along the line, y is negative 3/2. When you go along the line, y is equal to negative x, you put a negative x in here, that gives you plus 3x squared over the negative x squared is still x squared plus x squared is 2x squared. So that approaches 3/2. So that would be approaching, oh, I see what they're saying. This is approaching 3/2 up here, and this is approaching negative 3/2 down here. I see. You can't see it because it's behind the curve there. So that's what it's approaching. And those are completely different values. No way that's continuous, okay? Approaching two different values in two different directions, okay? But now here's the part I haven't figured out yet. Okay, yeah, we've done that part. Okay, so the limit of f of x at xy approaches 0, 0 does not exist, and you can conclude that f is not continuous at 0, 0. Okay, we did that. Therefore, by the theorem 13.5, you know that it's not differentiable at 0, 0. Yeah, we could have guessed that. On the other hand, by the definition of a partial derivatives f sub x and f sub y, you have the f sub x at 0, 0 is the limit as delta x approaches 0 of f of delta x comma 0 minus f of 0 is 0 divided by delta x. Okay? And that's the limit of zero minus 0 over delta x. How do they get that equal to 0? If delta x is approaching 0, then this would be going to 0. That is 0. That seems like it's indeterminate to me. Same way with that. I do not see how. I guess as long as it's not equal to 0, delta x is approaching but not equal to, and delta y too, that would be 0. Okay? So even though they have 0 slope coming in from whichever direction, and if you look back here, sure enough, that's the 0 slope, and that's the 0 slope. So, yeah, the slopes are 0, but just because the partials are the same, if they're going to different points, it's not continuous. Okay. So I guess that's what they're trying to say. Okay. Rather bizarre. All right, and that did finish 13.4. Homework exercises here. Do any of the odds 3 through 7. They're all at Calc Chat. 3 is at Calc View. Do any of the odds 9 through 13. They're all at Calc Chat. 11's at Calc View. Do any of the odds 15 through either 15 or 17. They're both at Calc Chat. There's an Exploring Concepts question 19. You can try that one. It's at Calc Chat. And then you have some application problems 21 through, goodness gracious, 33. They should all be at calcchat.com. Then there's a differentiability problem that's 30, do either 35 or 37. They're both at Calc Chat. 35 is at Calc View, and then do 39. It's at Calc Chat and Calc View. Okay. Do we have time to go to, to go to 13.5? Probably won't get much done on it, but let's at least go to 13.5. Okay. go from current slide. All right. 13.5, chain rules for functions of several variables. It seems like we've already used one or two already. Let's use the chain rules for functions of several variables. That's the first objective, and we'll find partial derivatives implicitly. Second objective. All right, so here's our definition. First thing up in 13.5. Let W equal f of x, y. So let's say W is a dependent variable of a function with two independent variables, x and y, independent. Where f is a differentiable function of x and y, and x is also a function of g of t, okay? And y is a function of h of t. So those are both independent or dependent variables of the independent variable t, but they are independent with respect to w. Where both g and h are differentiable functions of this new variable t. Then w is a differentiable function of t as well, and here's how you do it. Now, notice here, w is a sole dependent variable of a sole independent variable t. So therefore we say dw dt. Don't use a partial there because there's only one independent variable there. But with respect to x and y, those are partials. So the derivative of w with respect to t is equal to the partial of w with respect to x times derivative of x with respect to t. Okay? Plus the partial of w with respect to y times the derivative of y with respect to t, and you add those two together, and that gives you the derivative of w with respect to t. That's the chain rule, and it's shown schematically here. Okay? To go from here to there, this is what they're saying here. You first go partial of w with respect to x times the derivative of x with respect to t, add to that the partial of y with respect to the w with respect to y times the derivative of y with respect to t, and that gives you the derivative of w with respect to t. One independent variable, w, function of two, and I hate to call them independent. They said this wrong. One dependent variable. That's not independent there. Yeah. W is not independent. It's dependent. They've got a misprint in the book, and they got a misprint in on the slide set. W is a dependent variable. Okay? One dependent variable, w, is a function of x and y, which are each functions of independent t. Okay? Now, sorry about that. That's in the book as well. I'm going to mark out the IN there. Okay. They say in the book a proof of that theorem is given in Appendix A. Knock yourself out there. It also has this little, what do they call that? R something code in your text. The little box. RZ code? Huh?
It's not a barcode, it's
RZ code or R, something like that. Okay. QR code, that's it, QR code. So what you can do is do your phone on that, and it'll take you to that theorem proof, I think. I don't have my phone with me, so I can't show you. Okay. Do we have time for example 1? Maybe. Let's try it. Let w is equal x squared y minus y squared, where x is sine t and y is e to the t. Find dw dt when t is equal to 0. Okay? So we're looking for dw dt in general. And what do we say that was? Partial of W with respect to, I'm sorry, X times dx dt, okay, plus partial of W with respect to Y, whoops, times dy dt. Okay, all these are fairly easy to calculate. What's the partial of W with respect to X? 2xy. Okay, no. Partial with respect to X, that's a constant, and the derivative of a constant is 0. Okay, times dx dt, and what would that be? Cosine t, plus partial of W with respect to Y, x squared, minus 2y, right, times e to the t. Okay, E.T. was a movie. It's e to the t. Okay, never mind. Okay. All right. Now, the only trouble with that, it's a little messy because this W is expressed, the partial derivative of W with respect to t is expressed in x's, y's, and t's. You expect it only to be t, so we have to plug in what x and y are. So this is 2 times sine t times e to the t times cosine t plus sine squared t minus 2e to the t times e to the t. Okay? Let's see if we can make that make a little more sense. I don't think so. 2e to the t sine t cosine t. There is a way to shorten that a little bit. I doubt if they'll do that here. And this will be plus e to the t sine squared t minus 2e to the 2t. I don't know if that's any better. But it says evaluate that, find that when t is equal to 0. Okay, so dw dt, I can't write down there, okay, when t is equal to 0 would be what? What's that first one give you? Sine of 0 is? Sine of 0 is 0. Sine of 0 is 0. Cosine of 0 is 1. So since that's 0, this whole thing goes out. And since sine of 0 is 0, that one goes out. But here we have a minus 2 times e to the 0 is 1. So it's just minus 2. Yep, that's what it is. Let me clean that up a little bit. I thought it was going to take more room than it did. Okay, derivative of w with respect to t at t equals 0 is minus 2. Okay, once you're into this mess over here. Okay. Make sense? All right. Let's clear this out of the way. And let's see what they got. Okay. by the chain rule for one independent variable, you have the w dt is equal to partial w with respect to x dx dt plus partial w with respect to y dy dt. Okay? And that would be 2xy cosine t plus x squared minus 2y e to the t. Okay? But that has x's and y's in it, should only have t's in it. So go back and plug in what x and y both are and see what you get. And you get 2 sine t e to the t cosine t plus sine squared t minus 2 e to the t times e to the t. And that would be 2 e to the t cosine, sine t cosine t, so they left it in that form, plus e to the t sine squared t minus 2 e to the 2t. Just like I did. Surprise. Usually I don't do it the same way the book does. And when you plug t equals 0, this, well, sine t is 0, that goes away, sine t is 0, that goes away, this t equals 0, that would be e to the 0 is 1, so that would be a minus 1. Make sense? Now, all right, I think we're out of time, aren't we? So we'll start next time with this top of page 912. Now, homework exercises here, I think you can do any of the odds, either 3 or 5. They're both at Calc Chat, 3's at Calc View. I think you can also do 7 through 11. They're all at Calc Chat, 9's at Calc View. I think that's about it. We'll pick up the rest of these later. Okay? All right. Good deal. Any questions? All right. So you can stay put if you want to because your physics class is going to be in here. Or you can go to the restroom or whatever. Okay? Are you also in physics?
I'm in physics.
Huh?
I'm talking.
Oh, okay. All right. So I'm going to shut this down.